The idea behind the so-called crash clock emerges from a growing sense of urgency among space researchers who are watching Earth's orbital environment become increasingly crowded and fragile. For decades, outer space, particularly low Earth orbit or LEO, was treated as a vast and forgiving region where the number of active satellites was small enough that the risk of accidental collisions remained largely theoretical. That assumption is no longer valid. Researchers now argue that LEO has reached a tipping point, where density rather than distance defines safety, and where the margin for error is shrinking at an alarming pace. The crash clock is an attempt to translate that abstract danger into a time-based metric that is easier to grasp, much like the doomsday clock has done for nuclear and environmental risks on Earth. At its core, the crash clock asks a chilling what-if question. What would happen if satellites suddenly lost the ability to maneuver and avoid one another? In normal conditions, satellite operators constantly track spacecraft positions and perform collision avoidance maneuvers when objects come too close. These systems depend on functioning onboard electronics, stable communications with ground control, and accurate tracking data. A sufficiently powerful solar storm, a coordinated cyber attack, or a systemic technical failure could compromise many satellites simultaneously. In such a scenario, Earth's orbital infrastructure would effectively become a cosmic game of bumper cars, except at speeds of several kilometers per second, where even a small impact can be catastrophic. By modeling the current distribution of satellites in LEO, researchers calculated how long it would take before the first significant collision occurred if all spacecraft suddenly became inoperable. The answer is deeply unsettling. In a worst-case scenario, the first collision could occur in less than 3 days. This represents a dramatic acceleration compared to just 7 years ago, when the same kind of breakdown would have taken more than 4 months to produce a collision. The difference is not due to changes in physics, but to the sheer increase in the number of objects occupying similar orbital altitudes and paths. The crash clock's rapidly shrinking value is therefore less a prediction than a diagnostic. It reflects the declining health of the orbital environment. The explosive growth of satellite numbers is largely driven by the rise of megaconstellations, vast networks of satellites designed to work together to provide global services such as broadband internet. The most prominent example is Starlink, operated by SpaceX, which has launched thousands of satellites into LEO since 2019. Other companies and governments are following similar paths, planning constellations that could add tens of thousands more spacecraft in the coming decades. As of mid-2025, there were already around 11,700 active satellites in orbit, the majority of them concentrated in LEO. Compared to the roughly 2,000 satellites present at the end of 2018, this represents an increase of nearly 500% in just a few years. This surge has fundamentally altered the risk landscape. Each satellite occupies a specific orbital shell defined by altitude, inclination, and velocity. While space may appear vast, satellites tend to cluster in preferred regions that balance coverage, fuel efficiency, and atmospheric drag. As more spacecraft are packed into these regions, the average distance between them decreases and the probability of close approaches rises. Under normal conditions, this increased risk is managed through coordination and avoidance maneuvers. But the crash clock deliberately strips away those safeguards to expose how precarious the system has become. The danger does not end with a single collision. When two satellites collide at orbital velocities, they do not simply break apart, they shatter, producing thousands of fragments that continue to race around Earth at lethal speeds. This debris can then strike other satellites, generating even more fragments in a cascading process known as the Kessler syndrome. Once such a chain reaction begins, it can become self-sustaining, dramatically increasing the density of debris and making certain orbital regions unusable for years or even decades. The crash clock is therefore not just about the first collision, but about how quickly that initial event could trigger a broader, potentially irreversible collapse of orbital safety. Human spaceflight is also implicated in this risk. The International Space Station and other crewed platforms rely on LEO for operations, and even small debris fragments can pose a serious threat to astronauts. While stations are shielded and can perform avoidance maneuvers, a runaway debris cascade would make safe operations increasingly difficult. In the worst case, it could temporarily cut off human access to space altogether, grounding missions until debris levels decline, a process that could take generations without active cleanup efforts. The researchers behind the crash clock emphasize that it is not meant to be a prediction of imminent disaster, but rather a warning signal. The metric was introduced in a study uploaded to AR14, where it serves as a conceptual tool for policymakers, engineers, and the public. By expressing orbital risk in terms of time rather than probability, the crash clock makes the abstract more tangible. Saying that LEO could experience a collision in less than 3 days under worst-case conditions is far more visceral than citing statistical likelihoods that are harder to interpret. Aaron Bowley, an astronomer at the University of British Columbia and a co-author of the study, describes the crash clock as an environmental indicator for space. According to Aaron Bowley, the metric helps people conceptualize how little room for error now exists in LEO. Just as climate indicators track rising temperatures or atmospheric carbon dioxide, the crash clock tracks the growing fragility of Earth's orbital ecosystem. The faster the clock runs, the more stressed that ecosystem has become. One of the most striking aspects of the crash clock is how quickly it has changed. 7 years is a short time in the context of space infrastructure, which is often planned decades in advance. The fact that the clock has accelerated by more than 4 months in that span underscores how rapidly human activity is reshaping the space environment. It also highlights a mismatch between the pace of technological deployment and the pace of governance. International space law and traffic management frameworks have not kept up with the explosion of satellites, leaving much of orbital safety dependent on voluntary cooperation and best practices rather than enforceable rules. Solar storms deserve particular attention in this discussion because they represent a natural, uncontrollable trigger for worst-case scenarios. Powerful eruptions from the sun can disrupt satellite electronics, interfere with communications, and increase atmospheric drag, causing satellites to lose altitude unexpectedly. While most storms are manageable, an extreme event could simultaneously degrade or disable many spacecraft, overwhelming operators' ability to respond. In such a moment, the crash clock scenario shifts from theoretical to plausible, revealing how interconnected and vulnerable modern space systems have become. Cybersecurity is another underappreciated risk factor. Satellites are complex network machines, and as their numbers grow, so does their attack surface. A coordinated cyber attack targeting command and control systems could, in principle, interfere with collision avoidance on a large scale. While there is no public evidence that such an attack has occurred, the mere possibility adds another layer of urgency to the researchers' warning. The crash clock implicitly assumes a sudden loss of control, regardless of cause, and challenges stakeholders to consider whether current safeguards are sufficient. Ultimately, the value of the crash clock lies in its ability to reframe the conversation about space sustainability. Rather than asking how many satellites can be launched, it asks how much risk society is willing to tolerate. It forces a reckoning with the idea that LEO is not an infinite frontier, but a shared and finite resource that can be degraded through overuse. If the clock continues to accelerate, it may eventually reach a point where even normal operations become too dangerous, long before any dramatic worst-case scenario unfolds. The study's authors hope that the crash clock will encourage proactive measures, such as stricter debris mitigation standards, improved tracking and coordination systems, and investment in debris removal technologies. These steps could slow the clock, buying time and preserving access to space. Without them, the trajectory is clear. A crowded orbital environment with diminishing margins for safety, where a single failure could have cascading consequences. In this sense, the crash clock is less about fear and more about foresight. It translates complex orbital dynamics into a simple, sobering message. Earth's immediate cosmic neighborhood is becoming increasingly unforgiving. The rapid decrease in the clock's value over just a few years should be taken as a call to action. Space may still look vast and empty from the ground, but in LEO, the countdown has already begun.